Hello folks. In this video I'm going to cover examples from the geometric and the negative binomial distribution. A quick overview is we're going to talk about two easy examples, first from the geometric, second from the negative binomial, and then we'll cover another two examples, and these would be a little bit harder problems, so some moderate difficulty level examples from these two distributions. In the first example, let's consider playing roulette. Remember, in roulette, there's a wheel that spins around and a little ball that bounces up and down, and the number that comes up is wherever this ball lands when the wheel finally stops. So this wheel we'll assume has 36 numbers colored red and black, and then there's another 2 colored green. So there are 38 possibilities in this American roulette wheel. From what I understand, in European roulette, there's only one green slot, so a total of 37. But in American roulette, we have 38 slots. So let's say Smith is playing roulette. If he always bets the outcome that some number from 1 to 12 will occur, what's the probability that Smith will lose his first 5 bets? And part B, his first win will occur on the 4th bet. And then C asks, what distribution are you using? So remember, he wins when one of the numbers from 1 to 12 comes up. So the probability of losing a bet would be 26 over 38. Right? The probability he wins would be 12 over 38. Probability he loses is 26 over 38. So the probability x is greater than 5, we could simply take the probability of losing and raise it to the 5th power. You could see here we are using the geometric distribution, which answers part C. Now the probability that Smith has his first win on his 4th try is given by this product over here. I think of this. This is the probability he loses the first 3 tries, and then the probability that he wins on the 4th. So here we have these answers to the probability questions, and that completes problem 1. In example 2, suppose we have a weighted coin so that heads occurs with probability 0.6 and tails occurs with probability 0.4. We want to know what's the probability of getting the 3rd head on the 10th flip. Okay, so somewhat similar to a geometric distribution, but in a geometric distribution, we're interested in getting a certain first outcome, maybe a first head on the 10th flip. But here it's the 3rd head on the 10th flip. Okay, so if we let x be the number of flips required until 3 heads occurs, then x is a negative binomial random variable. And here we would say r is 3 and p is 0.6. So we have a nice PMF that we could use. Here the probability x is 10. We get 10 minus 1, choose 3 minus 1, which simplifies to 9, choose 2, times 0.6 to the 3rd, 0.4 to the 10 minus 3. So you could think of this, these are all the different ways where we could have 2 heads occur, okay, and then the remaining outcomes would be tails. And then I have the appropriate probabilities. I have 0.6 cubed, so this accounts for the probability of the 3 heads, and this accounts for the probability of the 7 tails. And we'll leave our probability like this for now. Okay, so those are 2 fairly straightforward applications of the PMF. Now, in this 3rd example, okay, well, let's say Edward and his friend cannot go to school when it's sunny outside because they're vampires. And not only are they vampires, suppose they live in Stony Brook, and Stony Brook is experiencing an extra sunny period. And there's an 80% chance each day that it will be sunny, and let's assume that the weather is independent from day to day. We let X be the number of days until the first day Edward can go outside. Notice that X is a geometric random variable. Number of days until the first day you go outside. So in part A, we'd like to know what's the probability that Edward will have to wait between 10 and 12 days inclusive to go back to school. In B, given he's already waited 5 sunny days, what's the probability his waiting time altogether is between 10 and 12 days inclusive to go back to school? And part C, what's the expected number of days he'll have to wait to go back to school? Okay, so X, as we said, is a geometric random variable. I want the probability. X is between 10 and 12. So we could treat this as 3 separate cases. The probability X is 10, probability X is 11, probability X is 12. The probability X is 10 is given by 0.8 to the 9 times 0.2. Right? We're going to have 9 sunny days, and then we'll have a day where the sun doesn't shine. Okay. The probability X is equal to 11 is set up. Looks very similar to what we had. It's just a different exponent here. 0.8 to the 10th times 0.2. And then finally, we have to add 0.8 to the 11th times 0.2. So when we work these out and add them all, here's our number, 0.0655. Now in part B, we're told, given he's already waited 5 sunny days, what's the probability X is between 10 and 12? Okay. But given this condition is really just like starting over due to the memoryless property of the geometric distribution. So we want this probability X is between 10 and 12, given X is greater than 5, okay? But since we have this memoryless property, this is equivalent to the probability X is between 5 and 7. It's almost like those 5 days do not matter. And now we could approach this probability same way we did up top. I have the probability X is 5, 0.8 to the 4th times 0.2. Probability X is 6, you see here, 0.8 to the 5th times 0.2. Probability X is 7, 0.8 to the 6th times 0.2. And if we were to work this out, we should get 0.1999. The expected value for X, E of X, we know has formula 1 over P, and this would be 1 over 0.2, which is 5. So that completes the third example. In this last example, we consider playing a video game. Suppose you vow to replay a tough level in Super Mario World until you win 3 times. Let's assume you have a 25% chance of winning each time you play, and each round is independent of any prior round. So we'll let X denote the number of times you have to play to win 3 times. Okay, and just let's make a note that each attempt takes 5 minutes. So in part A, we ask what's the probability you win your 3rd game on your 11th or 12th try? And in B, what's the expected amount of time needed in order to win 3 times. Okay, so our x is now a negative binomial random variable. We could calculate the probability x is 11. 10 choose 2 times 0.75 to the 8th power. Right, remember, there's a 0.25 chance of winning, so there's a 0.75 chance of losing. One must lose 8 times in this example, so I get 0.75 to the 8th times 0.25 to the 3rd power. So here's a good answer. If we wanted to take it and get it down to 4 decimal places, you can see this works out to 0.0704. Probability x equals 12 is fairly similar, but now I have 11 choose 2. We lose 0.75, well, probability 0.75 to the 9th power, times 0.25 to the 3rd. This works out to be 0.0645. And our final answer for A, we need to add these two probabilities. We come up with 0.1349. To find the expected amount of time, we need to figure out the expected number of games. So we have this nice simple formula for the negative binomial. E of x is r over p. In this case, it's 3 over 0.25, which works out to 12. It takes 5 minutes per game. So the expected time would be 12 times 5, or 60 minutes. So this concludes the video. I hope you've liked it.